with us as well. So Dr. Nick Fang is the Robert S. Gooch Endowed Professor and directs the Water Engineering Research Center at the University of Texas at Arlington. And he's a founding researcher at the Severe Storm Prediction, Education, and Evaluation from Disasters Speed Center, and serves on the technical steering committee for the Institute for Disaster Resilient Texas. And Dr. Fang currently also leads the academic council of the Interagency Flood Risk Management team for the USACE, Federal Emergency Management, FEMA, and the US Geological Survey and the National Weather Service to cope with extreme events and natural disasters. And he also actively performs research in the area for urban hydrology, radar hydrology, large-scale hydraulic modeling, and the radar-based flooding warning systems, flood resources planning and management, and also disaster mitigation. His exciting interdisciplinary research experience has gained national and environmental recognition through improving the fundamental understanding of watershed resilience by addressing two grand challenges of climate change and urbanization. And this morning, sorry, I will just skip that. His topic is right there on the slide, so you can look yourself. Let's save time and let's welcome Dr. Fang.
Thank you very much for the invite. I mean, I was actually presenting here before. I mean, not this is the same venue, but really excited coming back here again. So really, I mean, this is a very interesting theme this time because the organizers actually invited all the faculty members from the UTA, I mean, water resources. I mean, I know my dear colleague, I mean, Habib just presented his own research topic. I mean, I'm the second one right here. Hopefully, I mean, I'm not gonna ruin the expectation here, okay? But I want to actually see how many people actually graduated from UTA. I want to see people raising hands. Wow, my gosh, okay. This is a really, I think this is one of the reasons, I mean, we were invited. But I mean, I tell you, the one thing I want to do a little bit of marketing here is that UTA is no longer than before. I mean, it's really growing. I mean, really rapidly. And we do a lot of good research. I mean, and one of the things I'm going to talk about here is the TSI. I mean, it's a project. TSI is a transportation stormwater infrastructure. I mean, a lot of people thought I stands for integration, but legally this is called a really infrastructure. But so I just want to kind of quickly go into the slides, give you the reason why we actually started this project and what is the latest of the project so far. Next. Oh, okay, that's a bit different from my slide. So I want to click one more. I mean, this is a slide actually I stole from Jerry Cotter. I mean, he was the former chief of a water resources branch. I mean, at the U.S. Army Corps Force District. Can you click one more? Really, that shows all the, we called it this the Van Gogh painting earlier. I mean, it's really from 2010. I mean, it's from 2019. Or the historical storm happened in Texas. I mean, it's from 2010 to 2019, and that obviously covers tropical storm Harvey. I mean, there too. But that really kind of I want to show here is the massiveness of coverage. I mean, massive coverage of the storm over Texas. You may not really see the intensity. I want to kind of click on one more slide. I mean, next one. And I want to show something the needs of really the lack of resilience for all the infrastructure for Texas. So what you see right here is really showing all the historical storms. I mean, from way back. I mean, we use a kind of 24-hour duration. And if you choose a size of storm, 10 square miles. I mean, because if you want to classify storms, and you really need to consider about two things: is the duration and also the size of the storm itself. So if you actually really kind of choose all the storms from the past, I mean, historically, for 24 hours duration and this 10 square mile size, And then you actually plot them in a decent way, and you can see all the kind of storms from 2017, 19, I mean, and all the way to the earlier. I mean, basically that plot showing you here is most of the storms, if you see the gray zone, I mean, that is the current design standard for all the storms. I mean, and that's a TP40. I mean, basic back then before Alice 14, that was the main rely on the information for all the engineering design. And then later on, we have Alice 14. If we can click one more, I mean, I want to see the standard. I mean, NOAA Alice 14 basically raised the standard. Basically, that means really we needed to design all the infrastructure up to that standard. But even that, the gray line showing right there, we still have a lot more events way beyond, right? Higher than this standard right here too. So we have about 18 events historically, I mean, especially from the past 10, 15 years, that really kind of showing, hey, this is exceeding, I mean, the standard self. That actually set up a motivation of why actually we need to really rethink about the engineering design, I mean, for all the infrastructure right here. So click one more. And this is the kind of the news information. Actually, I was part of partially interviewed by the Washington Post by December 2022. Okay, and if you remember, 2022 and 2023, we have two. I mean, it's a long hot summers, right? I mean, and especially for 2022, we have the record of more than 100 days beyond the temperature above the 100 degrees. Okay, and but boom, I mean, by August 21st, I mean 2022, I mean, we got hammered by this basically is a big rainfall. I mean, the really the definition, the storm that time was considered about 100 year. Okay, I don't know if you people still remember that event. I mean, it's like really the current definition of the bigger flood is whenever people lower their guard, think about the drought still going on, then boom, I mean, the bigger flood just started right here. Okay, so that was a kind of a thing. I mean, the Washington Post basically showing the Deep Elm area in Dallas. I mean, that really got a hammered. I mean, it's a lot of high rainfall intensity and with a short duration. I mean, so we got a big rainfall event. Next. And I want to really show right here. I mean, so I think this is the kind of the zooming version of the Dallas area, because I mean, we can always take out a lot of floods for forwards if we have an ASC forwards branch meeting there too, but show some relevance. And that is a kind of August of 2022. I mean, the showing the river, the water in Trinity River just kind of so high right there. Okay, and that just kind of the downstream of all the reservoirs. I mean, in Dallas Forwards, and we want to basically show, hey, this is we are the title. The title of this news article is the U.S. is under the water. I mean, very scary topic. I mean, that motivation of that the article was basically saying all the FEMA inundation maps, okay, for the nation need to be updated because really not really representing the current risk, flood risk over the nation this moment, right? Next. And this is kind of we like to use the hydrology 101 and to show basically is urbanization making impact to the to these all the areas this moment. We know, I mean, for the undeveloped area that you have a higher percentage of evapotranspiration, and also you have a deep infiltration happens right there. So basically that lead to, I mean, the runoff is only 10%. I mean, current 10% from the rainfall, gross rainfall itself. But when the city is actually really under the rapid development, I mean, evaporation can be reduced and deep infiltration going to be reduced. And obviously somewhere in the mass balance equation, something going to really increase, which is the runoff percentage. So on the right-hand side, basically showing you, this is illustrative. It's may not be accurate if the city really kind of under rapid development could be kind of 55% of gross rainfall turning into the overland runoff. That is really kind of, in a nutshell, this is the causes of urban flooding at this moment. Next slide. And so this is the one thing I want to kind of show. We are actually sitting most downstream of reservoirs in Dallas-Fort Worth area. And there's a no, I mean, what you see, the red boundary is currently we call it the transportation stormwater infrastructure project boundary. And what you see right there is water actually really flowing to most federal reservoirs. And those are our first line defense, and really shows those are reservoirs actually protecting, I mean, the water actually from going downstream, and actually is showing us the protection right there. Okay. And but point here is those are reservoirs were built. I mean, it's decades ago. I mean, and I don't think at the time they actually building the reservoirs were considered about this rapid development happening in this region here as well. And I don't know if you guys still remember. I mean, so what is the current population in Dallas Force region at this moment? I want to just kind of raise a question. What is the size of a population currently? 7.5, okay, 7.5 million. And by 2050, I mean, or 2045, as a NCT cost projection, the population will be projected to 15 million. So that's almost like a double the current size right there. And where the people going to move to? I mean, those undeveloped area, right? I mean, so when people move into Dallas-Fort Worth area, two things they're really looking for is houses, where they're going to live, and that is going to really provide them the places, I mean, to show the stability and to work. The second thing they're looking for is water, okay? So you can see the challenges ahead of us here is the land development, how we got to do a kind of proactive planning, and also we got to seek additional water resources to support future growth at this moment. Next slide. So what you see right here is a kind of more close up. I want to show you this study area has about 85 cities, okay, and 8 counties involved right there. So while we have a more jurisdiction happening and make all the research engineering projects, I mean, very challenging because, I mean, people has always have different ideas. I mean, it's a policy right there. So having these kind of project going on in one concerted effort, that is a big challenge right there. And in this particular red boundary area, we want to actually say, I mean, currently we actually projected gonna have a 126% increase. I mean, the population, and I just roughly being translated into 2 million people kind of moving into this boundary right there. 2 million people gonna move in right there. And by 2015, I mean, this is a region about 60% developed, and in the by 2015. But also we know, I mean, the 19% growth happening from 2006 to 2016 right there. And so that actually shows, I mean, that this is the area is very dynamic, and also shows a great potential for more people to move in. And we also know the whole, I mean, study area right here is about 7,000 miles of a stream, and 274,000, I mean, says acres of the area within the 100-year floodplain itself. Okay, so I'm not going to go into this particular region. There are 2 sections right here. One is called the northern region. The other one is called the west region. Because the area is so big, we have to really kind of go into the 2 different phases, the west region and also the north region. And I believe that many people sitting here already be involved with the TSI project, because the project is so big, about a $10 million project over 3 to 5 years. And many different firms been kind of working on this project, and that is really kind of I would say this is a more I would say the project is never done before. I mean, it's unprecedented, and a lot of things we're learning along this way here as well. Okay, so next slide. I want to kind of show you, I mean, how this imperviousness really kind of changing over years. I mean, what you see right here is on the comparison between 2020, I mean, imperviousness versus the 2070 imperviousness as projected by City Cock. And by looking at it, I mean, basically you probably see, hey, the more growth, I mean, as a projected for 2070, I mean, I want to kind of click one more. And I want to show the difference between these 2 years. I mean, right there. That basically the color basically shows the imperviousness difference. I mean, in between these 2 years. And if I want to really kind of use the information from this middle tile into the hydraulic, I mean, format, I need to do a kind of area weighting. Next slide. So this is a kind of the delta of imperviousness basically being allocated to the individual basins right here. So if you see that one of the very fast growing basin, Maris Creek, I mean, you can see basically that area has about a more than 20% increase itself. Okay, so that is a basically 20%, 30% increase will really lead to a lot. I mean, the peak flow increase. I mean, so really, I mean, for engineering, I mean, especially if people sitting in this room, and we all know if you want to mitigate additional, I mean, peak of flow, and the best way for us to do here is really define a storage, because storage can mitigate a peak of flow, and that is a kind of a no-brainer. We want to really kind of see, hey, how big is the storage we needed to provide, and where those storage area we needed to really be kind of identify. We need to identify. So this is a part of our role, I mean, UTA, to really to optimize the storage size and also the spatial locations of the storage over the whole study area. Next slide. So I want to kind of show you, I mean, the direct impact of increased the land use data. I mean, this is the result part of this is the former, I mean, engineering project. I mean, my former Fund actually has a lot of involvement on this particular project by using a different kind of the land use data, and we can translate into really kind of the stage of frequency number. So that is basically showing this data actually is for the Bend Brook. I mean, we know the Bend Brook has a high risk, is a high risk of the reservoir so far. But if you factor, I mean, this increase the urbanization, you basically can see, I mean, the Bend Brook, I mean, the stage of frequency kind of go beyond the board right there too. The green line actually really kind of goes up. So that is basically showing, or the kind of urbanization is if we project up to 2070, I mean, that really going to overtax, okay? This is really going to overtax the current capacity, storage capacity for a lot of federal reservoirs. Next slide. So let's talk about the urbanization is going to impose a lot of additional runoff right there. But also let's not forget about the transportation, because transportation is a very important, I mean, routes in any urban settings right here too. And so all the land development happens. I mean, there's a transportation planning already done beforehand. And that is really the thing, show people, hey, where the urbanization going to happen. But meanwhile, I mean, you can see the transportation spending is very high and it's continue growing. And that obviously, I mean, if we usually, I mean, that the past planning always a transportation planner do their own job, stormwater people doing their own job, but barely actually they both talk together. And this is the TSI project. I mean, really is show us a proactive way for us to really kind of working with the transportation engineers and also working with stormwater engineers all together to make sure all the dollar sign being planned and also being projected, being well used while considering about a stormwater infrastructure itself. So that is one thing we actually really want to see. I mean, the cost of transportation is going to be very high, and how can we actually really work together hand in hand with the stormwater folks? I mean, to make this the future, I mean, the area, the DFW area, more resilient. Next slide. So this is the kind of I want to show you. I mean, the project itself. We have several partners. I mean, NCT COG, U.S. Army Corps. I mean, UTA. I mean, it's a Tarrant Regional Water District. I mean, and then we also have EWRI from 8M, because I mean, we have experts from a different area doing the very kind of unique, I mean, research itself. I mean, my colleague, I mean, Dr. Fuad Jaber, he is a bona fide, I mean, expert in the green infrastructure, because we wanted to really use many green infrastructure or nature-based solutions to really mitigate a stormwater increase for many different areas in this Dallas-Fort Worth region itself. Click one more. We have some words right here. So funding partners here is $10 million. I mean, obviously cannot be really drained out from one single agency. I mean, we have a Texas Water Development Board and the TxDOT and Federal Highway Administration and the federal FEMA money there too. But I believe, I mean, if I did not really talk about for the northern region, we have the general land office money there as well. So totally put these whole study area into the $10 million. I mean, as I say, I mean, we researchers are pretty reasonable. We don't take a lot of money, but most of the AE engineer consultants actually taking the most part. Jeremy, right? Okay. I just want to kind of so our job right here is we do what we've really been trained up to. We do a lot of optimization stuff. I mean, and so the idea here is largest scale study, and we're not going individually, I mean, manually to optimize this detention ponds for each subbasin, and we needed to do this a largest also, we needed to not only about the size of a storage, but also we need to find out not only the local optimal solution we need to find a global solution. So this is the kind of thing it needs a lot of a GIS exercise and working with the U.S. Army Corps to work with to get the best hydrological model and the hydraulic model as well, and to seek the best storage location and or the size of self as well. Okay, so this is kind of the optimization stuff is our own role. From UTA, we wanted to really kind of show you some the recent update. We wanted to kind of share that with you. Okay, next slide. So this is the kind of 4 different tiles, but really the process is a lot more complicated. It's a lot more complicated than those 4 different tiles. And obviously, we need to do GIS exercise and to really show the difference of imperviousness, between 2020 and 2070. And using these particular, comparison, and we ran, hydrological models that were actually is really developed by the U.S. Army Corps Forest District. And we understand the differences between the hydrographs, and that really shows the additional volume, being generated by this additional imperviousness. So the volume driven, and that really kind of is one of very important parameters in our optimization process. And this volume will actually need a comparable storage to accommodate this additional volume. That is a part of this the optimization process itself. And then we want to give a flexibility for optimization because you're not going to seek, a single answer from this one single simulation. You want to make sure all the optimization, for the storage based on the locations, and you need to actually give a certain range. So the optimization algorithm will eventually pick out a kind of a proper storage and also at a given location, still meeting the standard, which is the peak flow at a given location is not exceeding the existing condition itself. Okay, so on the right hand side, just show a kind of graphical illustration how those the global optimize the solution will be picked among those all the heights. You can see all the peaks right there as a kind of a local optimized solution. And then the solutions will be actually really mapped on a particular watershed, which in this case here is one of the pilot study area is Eagle Mountain area. And the coloration shows the different weights and different storage. And we eventually can really give advice or planning, planning advice for future, where we need to put a detention ponds right there as well. Next slide. So this is the kind of a high-level summary about this, basically how optimization's really done so far. And you can see the coloration is basically shows that, hey, for a given pilot study area, where are those the subbasins based on the optimization? We need to really put a bigger storage right there as well. And we done those the technical as advisory group meetings, and or we have a monthly hydrological small group meetings. The concept being kind of utilizing quasi storage in each basin and let an algorithm to really optimize or turn them on, turn them off, and based on the size of it, and to meeting these all the kind of eventually the solutions, and being kind of approved by different experts, engineers. And this is pretty good. One kind of questions from most people here is, can these particular, optimization algorithm to determine regional ponds or local ponds, the concept right here too. And I just want you to know, this is the kind of optimization still doing, and we will have a future update to determine where will be the best location to put those regional detention, there as well. So I just want you to know the takeaway of the slide here is these are optimizations not only going to give you a kind of specific size of it, it will also give you a best location of a put a storage detention ponds within anywhere, of the study area itself. Okay, so next slide. This is basically showing in a hack HMS model. So we were able to kind of turn on all the kind of detention ponds. Actually, we're putting them, and those detention ponds actually will be automated. To calculate for the best size and to really make sure those watch points. You can see those the 4 different watch points. Peak of flow is not going to go beyond. Their existing condition self. Okay, next slide. One thing here is for those are the regional ponds, actually, we are not actually really looking at a single watch point. Single watch point means we are not only say, hey, within this study area, we only look at the outlet. We actually work with the transportation engineers. So I think HAP associates work with the COG, really work on a lot of identify those critical locations within any area. We want to make sure those areas, are not going to be flooded, because optimization process may be actually, if you look at it, the most downstream location, and that may actually, the results may not really satisfy all the other locations not being flooded. So that's why we need to have a multiple locations to make sure all the peak of flow not going to go beyond their existing conditions. So those are actually listed. Those the West Fork area at different junctions. At those bridges, we wanted to use those locations as a part of objective functions in optimization. Algorithm itself. So what you see right here is if we're not going to do anything, theoretically, so to mitigate all the locations, the peak flow not going to go beyond existing condition, we need about a 6,210 acre-feet storage for this particular one, okay? And that is also listed about those different locations with their peak of flow. And so 6,210 storage is basically by theory, all the regulatory agency, they know, hey, if you're not going to go beyond a certain storage, go peak of flow, this is the kind of on the paper on this particular calculation, 6,210 acre-feet, that's what you really need. But our question here is 6,210 is really the final answer you will have? So the optimization algorithm can tell us. So that really can push the envelope and tell us can we really save a storage from this optimization algorithm itself. And the goal here, the answer I can give you here, yes, will be, because if you save on the storage, basically is saving money, right? Because we all know the storage costs every acre foot, actually costs money right here. Next slide. So if you click one more, I want to show the bigger picture of these. So the order of optimization went through about 40,000 iterations. Because you want to exhaust all the possibilities, and within this optimization, want to make sure we are not actually missing, okay, any solution from this possibility itself. So the objective function here is we wanted to lower the storage as low as possible, and also going to ensure the peak of flow is not going to go beyond existing condition right there. So the optimization being done in these 80 batches. And each batch we have about 500 different trials right here, and those are 40,000. 40,000 iterations. They were not actually done manually, really by the automated algorithm itself. And we'll actually want to show you some results. This is the option. Click on more. And we will actually also do the second layer of optimization based on these 40,000 iterations. We'll take, it's really the top 10% of all the optimized solution, do the secondary optimization, which that really can show you, the better results later. click one more. And this is the 10% optimization. We actually run another optimization Bayesian inference method itself. I mean, we just want to show you here. So what this particular slide here is the results based on the 40,000 iterations, and that treat all the possibility with the same likelihood, and which we know this is not going to be possible at all, but actually we have to do in the first round for the 40,000 iteration self. So on the left-hand side is basically showing you, I mean, all the weight factor we actually apply to these different kind of subbasins in self. And you can see, noticeably, you can see those high weight factors actually really happen to the headwater basin in this area as well. But the factor is not really means there's a storage. If we translate the factor into the storage, and the right-hand side basically showing you individual catchments, what is exactly the storage and detention pond you need to put right there. Okay, so I put it in the middle right there is we want to make sure the peak of flow at most outlets needs to be lower than 40,000 CFS, and the theoretically required storage is about a 6,000 2010 210 right there too. So by doing the uniform optimization, which I mentioned, all the possibility of the solutions are equal, right? I mean, so in reality, they are not. And they're basically showing, hey, we can lower the peak of value, even down to 39,191 CFS. And these optimization will give us the storage is about a 5,472. So yes, we can actually wash hands and clean our hands. Our job is done because all the 5,472 acre feet is lower than theoretical. Value right here. We gain about the 700-800 acre feet of storage, which is not bad thing. But we want to really want to push the envelope and to see if we want to use a Bayesian, inference method, what are the results going to really lead to us? Next slide. So what is the Bayesian inference method itself? Basically is what you see lower right, you see the three different kind of the probability, really the data distribution of it. Any optimization of mathematics itself is a kind of approximation of the true representation of the real world, right? So the prior beliefs is the red curve, okay? That is we use the uniform optimization solution to really represent our solution itself. But that actually still far away from the evidence. You see the evidence is the black line and still very far away. By using the Bayesian inference, we actually really will be kind of pushing these data representation of the solutions as close as to the reality itself. You can see these posterior beliefs actually is getting close to the evidence. So that's what this Bayesian inference optimization really does. Okay, next slide. So what you see here, people always say, what are you showing right here? Is basically showing all the subbasins in this study area, and with the multipliers down below, the right box basically showing all the color is a uniform color that represents the likelihood or probability of all the data. They are equal. And we ran about 40,000 iterations, and you get all the factors. Really kind of showing, hey, they share the same likelihood. In reality, shouldn't. And click one more. If you see, this is the this is the Bayesian inference method itself will actually show some basins, show some preference, and actually they will find out, hey, better factor or multipliers needed for certain basins itself. And using this Bayesian effort, optimization really helps us, to identify certain basins actually prefer. If you treat the subbasins as human being, and they have their own preference, okay? And this is what this optimization really can show you here. And you can see certain basin needs a higher factor. Certain basin you don't need to, because actually really not going to provide additional benefits itself. So this is kind of a show you, that in this very complex, sophisticated theory into a very illustrated way to show you the secondary optimization really can get us a better solution later. Next slide. So this is the kind of results, for the Bayesian inference algorithm. And you notice, if you're not looking at it, these are coloration of a distribution, these are basin, but simply look at it, the peak of flow gain a little bit. I mean, from 3,100, 39,100 to 39,700. I mean, but it's gaining about a 600 CFS for a large basin. 600 CFS gaining is not really noticeable. But the most important thing here is they are actually lower than existing condition. This is the very lower than the existing condition of a 40,251 CFS. But more importantly, what you really I value more on this particular solution here is by using Bayesian inference method, actually can really get us lower storage. At this moment, we just need to have a 4,881 acre feet will actually really gaining additional storage, save us additional storage on this optimization, right? And the pattern, spatial pattern of a required storage detention ponds actually very similar than earlier. And by using the secondary Bayesian inference method will actually help us. I mean, really can get us a somewhere refine our optimized solution self. So versus about a 620 10 acre feet theoretical required storage, and now we'll be able to really show, hey, 4,881 acre feet, that is a gain on the value on the project, the future project cost itself, okay? So that is the one thing I want to really kind of show you, the latest update of our study using an optimization method to identify the best solution of the storage, and also we can identify the catchments, where the catchments we need to put the detention ponds itself. Okay, next slide. Yeah. So this is kind of extend from what we do. I just want to kind of show a little bit here is outside of this the storage detention pond, what exactly we need to really kind of think beyond. So Texas, Oklahoma, and we know, I mean, the rainfall precipitation changes. Okay, I mean, it's a lot. And I know, I mean, being a governmental employee, UTA is a government and engineer. I mean, it's an institution. We're not allowed to say climate change. Being advised to call this is called a weird weather. But the reality here is the weird weather changing the rainfall pattern itself. That's why we need to enhance, I mean, our resilience, I mean, resilient plans. And we know the rainfall pattern going to change spatially, and the drought going to really happen itself. And what is the future holds in our water resources? Because this is the talk that really cannot be tailored for the EWRI. We all wanted to know the better environment and the water resources for this region and even for Texas. And let's also not forget about the water energy. Actually, they are in nexus, and you need a water, you need the energy. I mean, this is the one thing, I mean, I believe, I mean, Elon Musk, I mean, and one day he really mentioned in the next decade or so, two things are really going to be in shortage. One is power, because already people start driving, I mean, Tesla. They need a lot of electricity. The second thing here is water resources. I mean, those are the two big challenges ahead of us, okay? And next slide. And if you click one more, I just want to quickly go into, I mean, those different places. So this is population growth, no doubt, okay? Among the 15 different cities, I mean, so with the 15 fastest growing largest cities in the United States, I mean, that's the data from 2019, but I think this is that the rank is not going to change so much. Out of these 15, there are about six cities happening in Texas. And you can also count how many cities in Dallas-Fort Worth region, a lot, right? I mean, so think about a growth in the population, and those all need additional, I mean, water for us here as well. And those are kind of, we understand when I teach my water resources class, we know that each person, each day, you need about 110 gallons, right? I mean, that's the kind of the design capacity for most kind of water distribution and network. I mean, you wanted to put in right there. And with the millions of people moving, we need additional water, I mean, really to support people here. Next slide. I want to quickly kind of go into this is some recently published study right here. Just want to show for this the water availability. I mean, so for Texas, we have about all different planning zones right there, and we are in the zone C, and we want to look at the net water. I mean, it's a really net water availability, because net water availability is based on the rainfall, and we know also we need to subtract evapotranspiration and to really get a surplus or the difference between these is showing us, the future water availability. So the recent study we've done so far is we look at the decadal data from now 2020 to up to 2070. 2070 is a critical year. We also loaded 2070 for our TSI project, but for water availability, we wanted to use as a benchmark data itself. So people using two different kinds of the climate model, which is the moderate warming and also the extreme warming scenario, as they call it SSP 245 and also SSP 585 right here too. They both show different hot temperature in the future, and that got to affect, the water availability in the future as well. Next slide. I want to pick out the one zone, which is a region C. That's where we are. And so basically, you will see the good news about this is the water availability data showing here is based on the moderate warming scenario, we actually will have a 12% more water availability right here. But if you really wanted to use a hot model, it's a really extreme condition, you will see that about a 3% less. And you can see this is the study basically showing you, we use a CIMI 5 or 6 data and to compare that with all the projected data from a TWDB. And that shows the demand on the municipal area for region C is really going to increase significantly. And the positivity you see here is that if the climate going to really follow the moderate warming scenario, we have about a 12% more on the water availability itself, okay? And I want to also show where I actually came from, Houston area. I want to show the region H. Next one. So region H has a similarity. That basically, their water availability actually if follow the moderate warming scenario, is gonna have a 1% more. It's right there. But if you follow this hot model, this is gonna have a 4% less. So both regions has a high demand from the municipal area. And for Houston area, we also have a manufacturing and the livestock irrigation area. Those are the kind of demands from the water availability. So what you see right here, next slide, I want to just show you, the whole Texas, the climate region right here is showing if you moderate warming, it's that North Texas area will become a little bit wetter, okay? And for the on the west region, Rio Grande Valley area will be drier there as well. So the takeaway right here is the order we need to look out. A lot of several decades out to make sure we have available water for us. And that is one thing we really kind of been keen on. We wanted to make sure very proactive. Next slide. So this is the reason why actually we established our Water Engineering Research Center. And we just recently launched what we call WERC. It's gonna work, okay? And so really we handle a lot of challenges about the droughts, extreme events, and also we want to make sure all the human activities is not going to interfere. it's a lot of different kind of weather-related information. So the goal of WERC Center here is we wanted to really kind of debottle a lot of challenges happening in this Dallas-Fort region itself, and gain a solid knowledge and technologies, and to really apply to engineering applications. And we're going to work with a lot of private sectors, and these are the challenges not only for people sitting in the ivory tower to really address. We work together as a team and to really address all the challenges together, okay? Next slide. So one couple things, research and forecasting, what we do here is a part of this Inform Academic Council. Interagency flood risk management is also part of this WERC Center as well. We have a data storage and a rainfall storm. And Ramesh, we actually worked on together on the first Texas storm study we done last year. That was really the one actually we did on the Darth Valley, update all the Darth Valley itself. So storm surge, flooding, runoff, those are the kind of research thing we do here. And we want to actually really help. This is a Dallas-Fort region based on this WERC Center, and to really kind of help and to really be ready to embrace the future challenge in this region as well. Next slide. So with that, I'm just want to close my talk, and this is my team. And if you notice, one of the people standing in the crowd right there is a Jerry Cotter. I mean, as soon as he retired, we grab him to let him become the program director of the center itself. And we're gonna do a lot of things together. I mean, and obviously the center is growing, and we also kind of welcoming more people working with us. And there's gonna be a bright future ahead of us. Thank you very much.
Thank you, Dr. Fang, for a very interesting presentation. A lot of stuff, you lost me at the Beijing inference. But we are on time. Thank you, Dr. Fang, for making up the time for us. So we are on time now. So we're gonna open for questions.
With all the modeling that she did, looking at all the different areas in the Trinity Basin and Brazos for the optimal detention requirements, did you ever think about linking that to a digital terrain model to see if there's sites available at those points in the watershed where you have to have the optimal storage? I know I did regional detention in Austin back in the early 80s, and then it was just a matter of reducing the peak flows because of adequate storage or detention ponds that we had. We were able to make that work, and they actually incorporated that into their hydraulic design criteria around 1986 or 7. But did y'all link any digital terrain models to the models that y'all had to optimize these storages?
This is a very good question. I mean, the DTM at this moment, we actually focus on, based on the contract itself, we actually are really doing the optimization based on the hydrology itself. But I mean, the results need to be kind of a check and really kind of evaluated based on hydraulics, and also, I mean, the available DTM data itself, because I mean, the current thing here is, as I mentioned, I mean, where people actually is get the smallest budget of the project. I mean, Jeremy can do that as well for the hydraulic part. But as I said, we should, and that is also is a kind of a step before we actually really publish all the final results. I mean, and to identify those available location for the best solution right there as well. But we think about the current results we got here is give us a very the shorter range of selections, and that is a step number one. But we will have several sets of optimized solutions, and eventually we're going to pick one. So that's where the human being knowledge and expertise are going to come in to select. Yeah. Jeremy, be nice to me.
Yeah, I'll be nice. In your optimization routine, you're looking at modifying subbasin outflows, not like main riverine, like on the West Fork, for example. Can you clarify?
I would say, I mean, because that particular pilot study area has a pass through, right? I mean, the West Fork is really passing through right there too. So these are currently actually we strip off. I mean, it's really the main flow itself. But when we expand it into larger area, and those the riverine flow needs to be putting right there as well. Yeah, yeah, it's a very good question.
Hey, Dr. Fang, this is a regional scale, so I don't know the order of magnitude. The water we are drinking here, good amount of water, they are coming from different watershed, not from Trinity River watershed. Are you consider that factor in your model, which will drain to the Trinity River eventually?
So if I understand correctly, I mean, you're referring the TSI related project, but mostly, I mean, the TSI project, the water actually really coming from the Trinity River. But if the secondary, I mean, that's for the whole statewide, I mean, it's the climate driven. But I mean, if I understand your question earlier, your first question, those are water actually coming from the Trinity River.
It is? They're coming from the pipeline, right? East side or northeast side.
Oh, you mean the pipe?
Drinking water.
I would say, I mean, is that if we talk about the base flow, I mean, and recharge, those are, we do have some effluents from the wastewater treatment plants right there too. But those are part of the base flow condition. Yeah. Yeah. Yes.
Excellent presentation, by
Thank
the way. I wanted to know, what are the legal implications for detaining the stormwater runoff and capturing it with everybody eyeing the water that's going in there for future development, and they're really tied to maybe something else. So how have you thought about that?
So this is the kind of getting to the different realm before, I mean, above my pay grade. But typically, we know the water code in Texas is all the water runoff falling on the ground that belongs to Texas. I mean, that's a water code 101. But for these are TSI storage, I mean, project, I mean, I think this is the future design is we're not going to detain water. I mean, for permanent a long time. I mean, we have all the protocol to follow right there too. So this is the one thing, I mean, we're talking about. But I also wanted to kind of say one thing here is I think this is the one of the original goal of the NCT COX planning. I mean, they want to make sure certain detention ponds really gonna recharge it back to the groundwater, and that is another thing. I mean, we do need to consider more. I mean, how we going to better use this detained water and for many different areas. So the NBS nature-based solution does have an infiltration process going on. I mean, and if they want to facilitate additional deep infiltration, there is also another way we need to reconsider. We need to consider about it as well. Yeah. Sorry, I cannot give you a very, very specific answer at this moment. Yeah.